start the recording. Okay, hello everybody. It seems like that only two people has come to our lecture today. Thus everybody else will try to look it afterwards. So today we will be talking about strings and some algorithms on them. And we will start from the very simplest thing that you should understand how to work with is hashes. So we will talk about hashes. Today, this is our first priority today. So what is the idea for hash? Is that you have an object, you have a special function f that takes objects and puts it to long in such a manner that if you want to compare the first object and the second object, instead of comparing them as they are, we just simply check the difference of f of 2. So it is obvious from the left to the right if they're not different, or if they're different, then vice versa. If their function of O1 and function of O2 are different, then we can say that O1 and O2 are different. While if they're equal, you cannot be sure that they're equal on their own, because the function takes from objects to the long, and typically their set of objects, like the number of objects, can be infinite, while the long value is finite. So you can say if f of O1 not equals to f of O2, then O1 not equals to O2. This you can tell for sure. But if f O1 equal to f O2, you should compare O1 with O2. This is typically how hash map works, or something like that. Is that you have a different objects and you want to check how many of them are different. So you provide for each object two functions. You provide the hash code function and you provide the comparison function. And when you add an element to the array or to hash map, you just simply check if there is a same element with the same hash, then let me give it like a brief introduction here. So you have a hash map, and you want to put an object O. Then you take this hash function, hash of O, and try to add an element to this cell. As we already discussed, the hash can collide, but you can always check their elements on their own using the compare function. So instead of one element, per each hash, we will maintain the list of elements with the same hash. So when you want to put object O, you just take hash of O and pass over the elements and try to find O or add it as the new value. Then their exists of O, just again, we take hash O and pass through all their list of the elements with the same hash. So this is how hash map works typically in C++ or in Java. This is how hash map works. The only thing is to find the good hash function. That's the main question. How to find a good hash function that map a huge amount of objects to some finite space. Today we will be talking about strings. So for strings, one of the reasonable hash functions is polynomial hash function, and we will talk a little bit right now about that. So we will be talking about strings. So you are given a string which is S0, S1, S2, Sn. Like the simplest hash function that can come to your mind, for example, let's add all their characters together as integers, and this will be our hash function. Unfortunately, this hash function is not very good, because if you have like any permutation of these elements, then you will still consider that they're the same element, because their hashes will be the same. The alternative way, let me start finally from 0. Yeah, I think from 0 is better. The following hash function, S0 plus S1 times P plus S2 times P squared, plus Sn minus 1 times Pn minus 1. So hash of our string will be like that. This is their polynomial hash function of the string. So you take the character, each character, and you multiply the character by some value t, which is typically taken as a prime number. Which is bigger than the maximum value of the character itself. You can see that with this hash function, it is not trivial to like shuffle their characters to get an equal string or something like that. It is much more complicated. So, for example, if two hashes will be equal of different objects, the strings itself will be also quite different. And we can compare the strings simply by comparing the first character, and that's all. That will be enough to compare two strings. So as you can see here, I haven't told anything specifically for long, because our function maps the strings to longs, or like to integers, like as you wish. Right here, this value can be very big. So it is like 1 to 1. Right now, if P is bigger than Si, there are 1 to 1 correspondence between the value and the string. However, our final space is limited. So typically it is taken modulo special M. Modulo special M, where M typically is the huge prime number. For example, 10 to the power 9 plus 7. However, like these two parameters, where P is a prime number which is kind of small but bigger than S, and M is a huge prime number, it is said that this hash function is quite good. The only problem is that it is not very fast to calculate.
Vitaly, may I ask a question?
Yeah.
If we divide this hash function value for a huge number, we will have the value with a lot of numbers after float, right?
I'm not dividing, I take in modular.
It's modular.
It is modular.
Okay. It's clear, thank you.
Okay. So typically if you want the performance that we will talk further, you can take m equal to 2 in the power 63 minus 1. To be sorry, 2 in the power 64. Just forget about moduli and calculate this has functions in the logarithm in the logs. In the logs, as you can see, if you add or subtract or do anything with the modulo 2 in the power 64, it is the same as working in longs, as you don't think about the overflow at all. This will be the same. So let's write the algorithm first. So you have pow, which is equal to 1, and then you go for I equals 0 to n minus 1, do hash equals hash plus si times pow modulo n, and where pow is equal to pow times p modulo n. That's it. That's the whole algorithm to calculate the hash of the string. Please note that here I wrote it using modulo m, and I did modulo in both cases. You can see it, I did this because pow times p can overflow m, can be bigger than m, and this also can be bigger than m, and you have to make all your values less than m. Otherwise, you will get something overflowed with from the long variable. In Python, this is not critical because in Python all integers are big integers, but in the case of any reasonable language, however, this is important to not forget taking modulo anywhere as you can. So where you take m is quite good hash function. Where you have modulo 2 in the power 64, it is itself not very good function, and there are anti-hash test cases that takes two reasonable strings and compare them, and they become equal even by hash if you use modulo 2 in the power 64. So if you want to be sure that everything is fine, you can take, as we described previously. So to compare to strings, you just take string s and t, and you hash s equals hash t. Okay. If you want to be 100% sure that everything is fine, not 100%, 99 point something, you just create several hash functions with different p and different m, and compare not only one integer, which is the hash function for both strings, you just compare several hash functions at the same time. So, how to understand whether you're given the strings and you want to find the number of different strings in the set. So you have strings T1, T2, Tk. What are you doing? You just simply calculate hash of T1, hash of T2, hash of Tk, and you just ask their hash map to do everything for you. Okay. The next interesting question that will be very important for us is how to calculate the hash of the substring.
It depends on which alphabet we use in the string. We have to assign the value for each symbol in this alphabet and then calculate hash function.
This is the question, or this is...
No, this is not a question, this is answer.
Okay, no, like this is not the answer. So we have to calculate hash of Sij in of 1, where we can spend of n on pre-calculation.
We should remove one value from, okay, let's say we have to remove S1, S0 from this formula, and plus Sj, not S0, but Si minus 1, because we already know the previous hash, right?
No, that's the question. So you have, I don't think that you can come up right now with the right solution, so I'm going to explain it further. So the question is, like, you have all fun time on the pre-calculation, and you want to answer on any request, like you are given I and j, please give me the hash of the substring.
So the value of hash for this substring will be equal to hash for whole string minus hash for 1 to I and minus j to n.
Yeah, but you have to think about like powers of p. So you calculate, like, let me do the pre-calculation. So we calculate the prefix functions. So we will, like, we have two arrays, pal and hash. Hash itself will maintain hash 0 equal to S0. Okay, yeah, I made a huge mistake, unfortunately. I did the hash from the wrong part, from the wrong side. So let us do not this hash, but a little bit different hash. Sorry. So we will do this vice versa. So we kind of calculate like their smallest s is the smallest character has the higher power of p, and the rest are. Let's see. So what it is to calculate the hash function with substring. Let's consider. So it is s I times p I minus j. Oh, sorry. J minus y plus blah 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 plus as j at the end. So what it is, to be more precise, so you can think that plus sj plus blah 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 plus s0 p in the power of j minus p in the power, okay, this minus s0 times pj minus like this s I minus 1 times p j minus I plus 1. Probably I made somewhere mistake, but like that's not. We will think about this a little bit further. So you can see that what is this? Left. It is their hash function of S0j.
But we forgot about M here.
Ah, yeah. Let's do with M. So it is model M. Yeah. Typically, like, let's forget about M, but like, you can do this like that afterwards. Like right now, we are not thinking about M. Right now, we want to just say what is this polynomial function looks like. So we will add M further when we will write the algorithm itself. So everything that is here, it is hash of their prefix 0j. At the same time, this guy, what is this guy is? So if we put p j minus I plus 1 out of their brackets, so we just have 0p and there is some miscalculations or not. Okay, now everything is fine. S I minus 1. So we took p in the power j minus I plus 1, which is here. We took it outside the brackets. And inside, what is here inside?
Hash for s from 0 to I minus 1.
Yeah, exactly. This is hash for s 0 I minus 1. So kind of to get the hash for the substring, it will be enough to calculate the hash of the prefix minus some power multiplied by another prefix. So for that, we have to calculate the powers, this one, and their hash on the prefixes. Like let me make some adjustments, some small adjustments to make it more up to date, because typically when you ask, you don't think that J is in the right, belongs to the substring, so it's typical like that. So here is J minus 1. So here is J plus 1, J minus 1. J minus 1, and here it is that, plus I here, and finally it is like that. So right now is not there, like the right bound is not included. I typically write like that. So let us, do you need the code or you understand how to do that?
I think it's better to have code.
Okay. So here comes our pre-calculation. So this hash Paul. Let us say hash 0 equals to 0, and then Paul 0 equals to 1, then I take for e equals to 0 to n minus 1, I tell hash I plus 1 equals hash I times p plus s I modulo m, and here Paul p plus 1 equals to Paul plus 1 times p. So hash will now contain the hash of the prefix, and power will contain the power of p. So this will be very important for us. Now, and you can see that it becomes even less complicated than before, is that we simply multiply the hash of the prefix and add one more character. So if you can see here, so it is multiplying by p, this thing, and plus the new character. And then, so when we want to get the substring of I and j, it is simply return hash j minus pow j minus I times hash I. So this is the substring, the hash for the substring as I j minus 1. So you can see that our hash is tilted a little bit on 1. So that's why we have here j, not j minus 1, and here I and not I minus 1. Like, it's simpler for us because the hash 0 equals to 0. Like it's better not to write ifs, conditional statements. It's easier to write like that. Okay.
So when we add a new string, we pre-calculate all hashes for substrings and then can return its value for the constant time. Yeah.
You pre-calculate just for the prefixes. You pre-calculate the prefixes so that you can answer the substring in constant time. Oh, sorry. Yeah. Of course, you should take this modulo m. Yeah, thank you very much. I forgot about that. Also, you should add m one more time and take modulo m again. Why this is so complicated? The problem is that the first modulo m can be negative. And when you take a negative number modulo m in programming languages, you will get the negative number. So to fix this, you just add m and take modulo m again. Are there any questions? So, for example, we have a problem. We want to calculate the total number of different substrings of the string. How we can do that?
Can you please repeat question?
You want to calculate the total number of different substrings of the string S. How would you solve this problem?
We need to find unique hashes.
Yes.
We will compare hash and should compare two strings, right? I mean, we have to find substring in a particular string, so it means we have to compare this pattern, let's say pattern, with all substrings with the same length from this string, right?
Why pattern? You have to calculate the number of different substrings in string S.
Okay, got it.
Next, the straightforward solution for that is just pre-calculate all the prefix hashes and then go over all the substrings, calculate the hash in all of one time, and use the hash map for that. That's all. You just use hash map of integer, and like you just simply feed the hash map this the whole amount of different substrings. So it will work in all of n squared time because like the hash map works in all of n expected time. So thus you can iterate over all the substrings. You calculate the hash of the substring and put it in a hash map. Thus the total number of different substrings, or the total number of substrings is n squared, and you work with hash map in constant time. Okay? Like today we will do this a little bit faster rather than the n squared time. I hope that we will have enough time for that. So suggest another problem. We are given n strings, and you want to write the next function. You want to compare ti and tj. So you want to tell whether the string I less than string j or string j less than string I. So we are doing this like so that you understand why I'm trying to do this. We will try to do sorting algorithm for the strings, which can be a little bit faster than calculating in straightforward manner. So, how to write this comparison function? Okay, we have this string ti and string tj. What is, like, how to compare two strings? You just go one character by one character, while the characters are equal. And then at some point, some character is different, and here you find your comparison, whether tj is bigger than ti or ti is bigger than tj. It is just simply to compare the first character that differs. It is obvious that the running time of this algorithm is it is minimum of ti and tj, the lengths, minimum of the lengths of two strings. I would like to do this faster, but with additional pre-calculation. So again, I pre-calculate all the prefix hashes for each string. Okay, so how to calculate the comparison here? To calculate the comparison, we should find the longest prefix that is equal for both strings. Let's do this using binary search. So we know L and R equals to ti tj plus 1. And we simply have to find using binary search. So at first, why we can use binary search here? At first, all our strings are equal, all the prefixes, and then suddenly the prefixes become different. So that the function has only two answers. Either they're equal or either they're not equal, and luckily it is monotonic. So at first it is equal and then they're not equal. So while L less than R minus 1, do we take M, which is equal to L plus R over 2, and if hash at ti and 0 n plus 1 equal to hash tj 0 n plus 1, then you can say that L is equals to M, else R is equals to M. So left will always point to the last character that is equal, and R will point to the first character that doesn't. And here you use the prefixes for their substrings. What is the complexity of this algorithm? Can you tell me? Of this comparison?
Minimum of this log of minimum ti, tj.
Yeah, so it is simply of logarithm of this. Okay, now suppose that all the strings here have the same length. And we want to run the sorting algorithm on it. What is the complexity of the sort algorithm will be here?
So we compare strings with equal length, yeah?
Yeah, so we know that the length, like, it is, because it is, okay, or for example, that the length of the substring is not bigger than L. Okay, let's do this.
Or logarithm L.
How can you repeat?
Logarithm L.
No, this is one comparison. Like, suppose we use merge sort or like other fast sorting algorithm. What will be their total complexity of the algorithm?
Oh, can you repeat this?
Suppose we want to run a sorting algorithm on it. So we know the comparison function, which works in logarithm L time. What is the complexity of the sorting algorithm will be if we sort using merge sort?
L multiplied by logarithm of minimum of length of string.
No. Okay, so we have n strings. What is the complexity of their merge sort if we had integers? You want to sort n integers. What is the complexity of merge sort?
And log n.
N log n, okay. Okay, so let's start with the first. N logarithm n. Okay, then how many comparison functions we called during the merge sort algorithm? How many times we ask compare function? Is it different from n logarithm n?
L times.
Where do you take L? Like, how many times, like, you sort the array of n objects, and you have a comparison function that compares two objects. How many times the comparison function is called?
Log n.
No, keep thinking. Much bigger than log n. I can surprise you, the number of comparisons is n logarithm n. I have a tier here that slightly goes down and down. So the total number of calls to comparison function is n logarithm n in Mercer. Then, since we know that one comparison function works in logarithm L type, what is the complexity of the algorithm? Again, how many comparison functions do we call? We call n logarithm n comparison functions. What is the complexity of comparison function of the strings? We talked about this right now.
Logarithm of maximal length.
Yeah, logarithm of L. Then, the total complexity of the sorting algorithm will be
And logarithm of L.
It will be n logarithm n times logarithm L. You have n logarithm n comparisons, and each comparison works logarithm L. Thus, the complexity is the multiplication of these two. Then we can sort all the strings in such time. Okay. As I already mentioned, we are trying to solve the problem how to calculate the total number of different substrings of the string in which works faster than squared time. So we already talked how to do this in squared time using the hash map. So you simply traverse over all the substrings, calculates their hashes, and ask for hash map whether this hash exists or not. How to do this? present you one of the most important kind of things in string algorithms, which is suffix array. You just take the string S and you want to sort all the suffixes of this string. So for example, ABA, CABA. What are the suffixes? Suffixes BA, CABA, ACABA, CABA, ABA, BAA. So these are all suffixes. Okay, so we want to sort them. What will be their resulting what will be the resulting string? So like we add additional character as dollar to the end of this. Then it will be a dollar, then it will be ABA dollar, then it will be ACABA dollar, then ACABA dollar. So this. Then we have two substrings that starts with B, so this is BA dollar, BACABA dollar. And finally, one suffix that starts with C, it is CABA dollar. Why suffix array is important? Suppose that we sorted all the suffixes, like as we did here. How to calculate the total number of different substrings? Each substring starts from some suffix, from the beginning of some suffix. For example, ACAB starts here, ACAB. So, let us calculate for each pair of the suffixes in this order, calculate the longest common prefix. So here is 1, so here is AA, here is 3, here is 1 again, because there is only A and B different from C, here is 0, here is 1, and here is 0 again. Why it is important of this largest common prefixes? So this is known as LCP. LCP, largest common prefixes. What does it mean to have, for example, 1 here? It means that the substrings that starts here with the length 1 already happens before. But all other substrings, like that end after this equality, like AC, ACA, ACAB, ACABA, and like ACAB dollar, is other strings that we haven't calculated yet if we go from top to bottom. So we go from top. okay, we have the string A, which is one different substring. Then we take ABA. Okay, A already the same substring because like it has like LCP1, but at the same time, AB and ABA we never encountered before. Thus, we can add the number of length of what it is, S, I don't know, S, let it be S1, S2 minus LCP between S1 and S2. Then we come to the third substring. So we know that their LCP is 3. It is here. And we know that all the substrings that start with this suffix, but which are small enough, already happened before, so we already calculated them previously. Then, all the other substrings that starts at this character, we haven't encountered it yet. So we can add ABAC, ABACA, ABACAB, and ABACABA. So it is again S3 minus LCP, S2, and S3. And so on. Thus, the total number of different substrings will be equal to the sum of all the lengths minus the largest common prefixes there between each consecutive pair. I will let you think a little bit. Like, do you have any questions up to this point? It's a little bit complicated, yes. Like why we can use this with this LCP? We can use it because all the suffixes are sorted. And if we haven't encountered the larger substring before, then it hadn't been there. It hadn't been anywhere else. It can be only at this position.
Natalia, can you please repeat what these calculated values means? I'm not sure.
Okay, so you mean this calculated values 1, 3, 1, 0, 1, 0.
No. What about S1, S2 minus LCP? These values.
Okay, so we consider the first suffix. We never seen all the substrings that starts with this suffix. How many substrings that starts with the suffix of length S1? They're exactly length of S1 substrings. So for example, here it is only A. So it is one here. Then we take the second suffix in their sorted order. We already calculated, like, we take LCP for this two substring, which is 1 here. So we know that all the strings that are length less than 1 but starts at this point, they are already calculated before. For example, here it was only A, and we already calculated A before. But AB we haven't calculated yet as a different substring. And ABA we haven't calculated. This is exactly like S2, like the length of the second prefix minus the LCP between these two prefixes. So S2 minus LCP between these two. Then we come for the third. We found an LCP equal to 3. Then starting from position 3, all the substrings of this prefix, of this suffix, we haven't seen them. So we have seen ABA, AB and A before, because this LCP tells us. But we haven't seen ABAC, ABACA, ABACAB, and ABACABA, which is LCP of, like, thus it is the length of S3 minus LCP of S2 and S3. Like, if we continue with the next, so it is S4 minus LCP, S3, S4, and etc. And then to calculate the total number of different substrings, we should add all these numbers together.
Okay, now it's clear, thank you.
Because this is due because all the substrings are visited here. For example, the substring that starts at position I, like substring Sij, it is simply the prefix of the corresponding suffix. So it is the prefix of Sin, which we calculate. So for example, this was Sin, and here is the prefix, like the prefix of this thing is what we want. Like, by that we kind of calculate, we kind of go over all the substrings of the string using this. So let's summarize a little bit with the complexities. So at first we need to get a string and get a suffix array out of it. Suddenly we already have everything what we need. We have the substring, like we know how to calculate the hash of the substring in constant time. Like, it is no different than compare S0, Sn minus 1, S1, n minus 1, S2, n minus 1, Sn minus 1, n minus 1. So these are n different strings. And as we sorted them before, we already discussed their algorithm that sorts the different sorts the strings. We can sort these strings in O of n logarithm n times logarithm L. But what is L here? L is n. L is the largest suffix here. So the total sort of all their strings is n logarithm squared n. That's how you get the sorting strings. Like using our algorithm for the sorting of strings, we just get the sorting array of their suffixes. So we get suffix array. Then we know their identifier of each suffix here. And we are asked, what is the LCP between two suffixes? This can be done using our previous algorithm, because LCP is exactly the longest common prefix. We already know how to do that in logarithm time, using binary search. That's what we did there. So, to summarize, we sort all the suffixes, then we go one by one and calculate their largest common prefix of each pair, okay, each consecutive pair. And then their total number of different substrings will be equal as their sum of all the lengths minus their LCPs. Okay, do you have any questions? Anything else to repeat probably, or?
So by result, we will have a total number of unique strings.
Yes, exactly.
Yeah. Okay.
Like, in total, the complexity will be of n logarithm squared of n. However, there are algorithms to calculate in linear time, which are much more complicated than the thing that I described right now. Okay. If you don't have any questions, I will move forward. So, like, this is their highest peak of the complexity for today's lecture. Okay. Okay, let us continue with the simpler problem. You are given string P, that is pattern, and you are given string T, which is text. The question is, where is P inside T? How to do this? In the time P plus T. So you want to check whether the pattern exists in the text in linear time. Can you do that?
We have to calculate hash of this pattern and hash of each substring with the same length of.
Yeah, exactly. There is nothing complicated here. Yeah, you just calculate the hash of P and calculate all the like hashes of the substrings. You already know how to do that. Of the substrings with the right length. Okay. A little bit more complicated problem. You're given strings t1, t2, tn, and you have to find their largest common substring. So we want to find a substring which exists in all of these n strings. Can you come up with the algorithm? Let us start from any algorithm that will come to your mind. Even let us start from is there exist does there exist a common substring of length L? That's probably the first question that will guide you to the solution. Is that how we can check whether there exists a common substring of length L?
We will calculate hashes for all substring, this length for each string, and in case it will have same value for this hash, we can say that they have the common substring.
Okay, how are you go? So you calculate all the hashes of all the substrings of length L.
Right.
Then how do you choose the common subset out of them?
For example, we can create the list of hashes, and then we will find the common value of the hash. And in case
I don't understand. Sorry, I don't understand. So you have like hashes of T1, hashes of T2, hashes of Tn. So you have array of string, array of list.
For example, we have an array, and then we have to find the same value.
Yeah.
Which presented in each of this array.
Yeah. How are you going to do that?
We can merge all the hashes, then sort it, then fold every hash to hash and multiplicator, which means how many times this value is present in the wall.
No, this will not work. For example, if one string happens in the first string several times.
Yeah.
But it should be presented as minimum n times.
Yeah, but this is not enough. If it is presented n times, you cannot be sure
yes,
that the
yes,
substring
because,
is.
yeah, I got it.
If I think we can intersect them, but maybe we can sort them and compare the positions.
Okay, yeah, we have to intersect this two. Yeah, that's true. We have to intersect them all. So what is the simplest way to intersect them? We sort the first array, we sort the second array, and we go by 2 pointers whether the elements are there. The more simpler solution will be to use the hash map. So you put all the elements of HT1 into hash map, and then you try to add all the elements of HT2 and create a hash map of only elements that are present in the first map, and so on. So you can use it you can use the standard algorithm, and it will work in the linear time depending on all their lengths of the substrate. Okay. So since we understand how to answer this question, how to solve the problem,
Oh, as Ekaterina said, we calculated all the hashes for substring for all t. So we get hashes, array of hashes ht1, ht2 when we calculate if we have intersections and we choose one that is longest. But how?
okay, what is the complexity of your algorithm?
So do we say that we need all substrings? Let me just calculate all the substrings we want.
Yeah, you just have to calculate all the substrings and do something like that. So it is at least depends on the square, square of the length of the string. So it is, in the best case, it is t1 squared plus t2 squared plus tn squared. Yeah, and then you have to apply this, yeah. So it is long enough. It's quite large. Can we do this faster? Again, so the problem is find the largest common substring. So you know how to, typically I will give you the question and probably it will give you the answer. If we know that
we can maybe use principle of binary search when we from 1 to L, and we're using this principle. So we do it in log n time.
Yeah, exactly. So you can use binary search here. Why you can use the binary search? Because if you find the longest common substring, if you try, all the smaller substrings are also common substrings. So if we found for length L the common substring, then for all smaller lengths we also have the common substring. And vice versa, if we don't have for a substring of length L, then we don't have a substring of high length. So this function, the function is again have only two values, and it is increasing. So it is like that. So we can run binary search over L, and then for L we calculate we run this program, kind of, that answers does there exist here common substring of length. So in total, you will have the algorithm that works in linear time, like the linear time over the sum of whole lengths times logarithm maximal length of their string. Okay. To be honest, that's it for today. So if you have any questions, I'm happy to answer them while we still have time. So I gave you a brief introduction into strings. So like hashes, if you understand hashes, you could solve almost all the problems in strings in reasonable time. So we don't have time to come over all the possible string algorithms, but you can use, like, typically it is enough to know hashes. Okay, if you don't have any questions, thank you for coming, and the next time we will be talking about graph algorithms.
Thank you very much.
Okay,
Thank you.
see you.
Thank you.